Welcome back to ECE 340. The discussion prior to beginning was the buzz was on exam number 2. That's in a week. And before that happens, you need to make sure and get 2 homeworks turned in. Homework 4 is due today, and homework 5 is due on Tuesday, which is the next time we meet. There are some summer opportunities as far as research opportunities and internships that I've posted on the D2L website for this class. You might look at the news page or the front page. Hopefully you can find that information if you are interested. And that might provide you something to do this summer if you're not reviewing or continuing to work 340 problems. I didn't take a vote. I just said, let's go ahead and have it because I have a lot of other things going on. Is this a problem if we start a few minutes after 5 next Tuesday for the review? The IEEE president, the president of IEEE, will be in the room up until 5 o'clock, and I don't want to kick him out. And you might want to even come and see the president of IEEE, but we will then have our review session at 5:15 after that, and I will try to record that and make that available on the website. What we want to do today is talk about Bode plots, and we'll quickly go over the transformation process. Then we will get into sketching individual terms. We'll look at having a quiz to see if you're getting some of this. We'll jump into linear factors and be able to worry about Goldilocks at that point. And then we will see how we can convert complex factors to linear factors by some rather crude simplifying assumptions, but at least that allows us to fairly quickly do these straight line sketches for the different terms that are a possibility with respect to these transfer functions. Here is our transfer function that we had last time. Maybe we didn't display it in this form. This form is useful in figuring out how many poles or the order of the system. And we look at the highest power of S. This is really a ratio of polynomials. We have a numerator that's of first order. We have a fourth order denominator. And maybe that's about all we can tell from that formulation, and it might be nice then to identify the poles and the zeros, and we talked about how we could do that last time on your calculator or in MATLAB. I think it's pretty clear that the numerator has 1, 0, and it's located when S is equal to -10. The other polynomial, the denominator polynomial, may not be quite as obvious. The first one hopefully is. If you simply see that you don't have a constant term, you can factor one of those s's immediately out, and now you have a cubic, and you could find the roots of that cubic. If you do that, you will end up with finding out that you have 3 more poles, one at -0.1 and 2 on top of each other at -100. That's the same transfer function that we started with before when we were talking yesterday about sketching Bode plots or identifying the different kinds of terms that might be possibly in a transfer function. With those poles and zeros identified, the denominator was already monic, meaning the highest power of the S term had a coefficient of 1, and we can then simply write down its factored form. The numerator, we can pull out the 10, and now we have a gain term, the zero factor, and the pole factors explicitly identified in the pole zero form. But as we said last time, that's not the most efficient way to think of the transfer function if you're going to be sketching a Bode plot. What we want to do is convert it into a time constant form, and we can do that by pulling out all of these values for the poles and zeros that are sitting over there in the constant term. We factor out the 10 upstairs, we factor out the 1/10 downstairs, we factor out a couple of 100s downstairs, do the appropriate cancellations, with which, if you're paying attention and looking at the colors, you can maybe see how that was done. But effectively, we are left with a constant term of 1/10 in that transfer function. That boils down to then a constant of 0.1. We have the pole at the origin explicitly factored out. And then we have these other three terms that are factored in such a way that there's just one S in each of those factors. Just remember that there's two identical factors of S over 100 plus 1. And we're just collapsing that down with the squared piece. That's the linear factor, and this is then the time constant form. And I'm going through this quickly because we've already done this. Then we look at those terms. The only term that was missing is what's number 4, but the first three terms were in that example. We had a constant term, which was 0.1. We actually had a pole at the origin. We had a 1 over S factor or term. And then we had 1 0 factor, meaning you would have something like this quantity S over Z plus 1 upstairs. That's our 0 factor, and up at the example, the Z was 10. That's where our 0 was located. And we had 3 pole factors that had that structure associated with them. What we didn't have explicitly was this complex factor, which we now are writing a little bit differently than what we have written before. Now we're basically writing it in terms of a distance away from the origin and an angle. And then you have its twin downstairs. What you'll want to do, though, is make sure that whenever somebody gives you a quadratic, make sure it really corresponds to complex roots. If you can factor it into real roots, then you simply have 2 real factors. If you can't factor it into 2 real roots, then you have a factored form like this, where the zeta is living between 0 and 1. If it can't be factored into 2 real factors, then you have this complex factor, and that's what we'll talk about at the end of this discussion. How do we deal with that complex factor in sketching the roots, and how does that zeta play a part? The natural frequency, or the distance those poles are from the origin, tells us the frequency content, or the frequency information, or the break that's associated. In this case, if it's in the denominator, that's a pole factor, and once we hit this omega sub n, we're going to be sliding down. Since it's really 2, or a second order factor, we're now going down at twice the 20 dB, or we're actually sloping at 40 dB per decade. Last time we even got as far as looking at the constant term, which, if it's a k, whether that k is 5, whether it's -2, whether k is 27, it doesn't change with frequency. It didn't have a frequency dependence. There was no omega anywhere in that gain piece. Because of that, then this magnitude in dB, which we simply take 20 log of the absolute value of that gain value, that's just a fixed number for all frequencies omega, and that just gives us a piece of our entire Bode plot that is constant. And if you sketched everything else and then you said, oh, I've got to worry about a constant, well, that constant really just shifts your magnitude up or down depending on whether it's bigger than 0 or less than 0. So if you failed to incorporate the constant in sketching your Bode plot, I wouldn't start erasing anything. I would just say, oh, now I need to shift everything up by whatever this numerical value ends up being for all frequencies. The phase is similarly maybe benign or boring. The phase is either one of two values for all frequencies, depending on what k is. If k is non-negative, then the angle is 0. And you can sort of think of that in terms of having a complex number k, and if it was simply a positive number, you would be in the positive right real axis, and there's no angle between that and the origin. However, if you're in the negative, your angle relative to the positive real line is now either plus 180 or minus 180, and we'll just assume for consistency in everyone's answers that we'll call that minus 180, and that corresponds more to a delay in time. Questions so far? If we carry that through on an example, let's say that somebody says, oh, your gain k in this particular case is 5. Then we can simply compute 20 log base 10 of 5, which 5 is less than 10, and log of 10 was 1. So you should anticipate the log of 5 being bigger than 0 and less than 1. It's 0.7 roughly. 20 of those gives you a 14 dB. Now you have, if you were sketching this, and my frequency axis is way over there, but it's this axis, here's 1, 10, 100. Those are equally spaced because we are using a semi-log horizontal or independent variable axis. We usually label this as omega, but it's actually representing the log of omega. Meaning if you now said, oh, here is 1 and 10 little squares later is 10, then if you needed to find 5, you would say, oh, that's 70% of the distance between 1 and 10, so you would count over 7 of these little squares, and that would be your 5. And what you may want to do, just to get comfortable with this, is look at what all of these values are. If you took the log of 1, that's 0. Log of 2, what's log of 2? Isn't that about 0.3? You could do that on your calculator, and now you're 30%. You're not 20%. If you're thinking this is the semi-log variation in terms of this is the log of omega. Now when you go from 1 to 10 and you want to go to 2, you've now moved 30% of the distance between 1 and 10 on that logarithmic axis. That's all I'm wanting you to keep track of or to realize. With a magnitude or a gain value of 5, that's a real number. It's positive, that has an angle of 0, and now if you simply sketched an axis on the exam, I might even give you full credit for it because I couldn't tell whether you really had a line drawn on top of it or not. So it might not be a bad idea to at least start sketching some axes occasionally. And then if you had multiple pieces, maybe at least you've gotten one piece of that right, which is the constant piece's angle, right? And that represents then the phase of h sub 1 of j omega, which we said, oh, for this example, let's just let h be 5. That's the first case of these 4 different possibilities of cases that we can have in sketching Bode plots. Let's now look at the second case. Which are poles or zeros at the origin. Suppose that we now have h sub 2. Well, let me put it in terms of S first, and then that's maybe how you're more used to seeing it. You could now have h sub 2 of S as some S, and then we could represent this either as zeros or poles by raising that to a plus or minus n power, capital N. In this notation, the positive exponents would represent zeros, and the negative exponent, which would put S effectively downstairs, would be representative of poles. If we were then looking at the frequency response, we then have S replaced with j omega, and we have this j omega to the plus or minus capital N, where N represents the number of poles or zeros that you have at the origin. If we now wanted to look at the magnitude, whoa. Again, we're doing that in terms of dB. We're saying we're taking 20 log base 10 of the magnitude of j omega to the plus or minus n power. How does j impact that magnitude? It doesn't, does it? The magnitude of j is 1. So we can get rid of that magnitude sign and j if we want and just call it omega. And now we have, and the other thing that's nice is since we're dealing in dB and taking the logarithm of this argument, now when we have the argument containing exponents, that exponent flies out in front. And now we can have plus and minus 20 capital N log of omega. And that's exactly the same expression, meaning we can now say that this magnitude looks like that. And again, this is a logarithm base 10. Plus means what? Zeros. So this now, just think what this is representing. This log of omega, if you remember what we were doing before, that was our independent variable axis before. This was this log of omega. Meaning this piece right here is, when we're sketching this, this is actually our independent variable. And if we were thinking of this as, oh, the left-hand side is some vertical number, then if you think of this like a straight line, where x is your independent variable, now we have something times our independent variable. This is just a straight line. Whether it's going up from left to right or down from left to right is determined by whether we are starting with zeros or poles when we're looking at these things at the origin. What we now have then is a straight line and maybe somebody says, oh, you had 1 0 at the origin. Capital N would be 1. Now we know we have a slope of 20 dB and it's going up. Now we go, well, how do we locate that? Where do we pin it down? We need to figure out a convenient value of omega that has a nice, let's say, y or vertical component. And a nice value would say, oh, let's look at when omega is 1. Because we all know that the log of 1 is 0, and 0 times anything is 0. So we can now say, oh, the vertical height will be 0 when omega is 1. And that gives us a way of pinning that sloping straight line down. That line never breaks, it's always sloping. And that's because it's a pole or a 0 right at the origin. We're then looking at sketching a straight line passing through 0 dB, and you just told me when that happens. That happens when omega is equal to 1 radian per second, and we have a slope of plus and minus 20 n dB per decade. What's a decade of frequency? What's a decade in time? 10 years. So a decade of frequency is a factor of 10. When we start talking about a decade, then we're talking about a factor of 10 in frequency. If I said, oh, I'm at 2, go a decade beyond 2, you would be going up to 20. If I was now at 35 and I said go a decade beyond that, you would now be going up to 350. That's a decade change in frequency. So this decade of frequency is simply a factor of 10. Now sometimes you may not want to go that far. Maybe you just want to look a little closer than a factor of 10 from where you presently are located. A smaller or shorter distance is a factor of 2, and that's an octave. And instead of going up and down by 20 dB per decade, if we're just going a factor of 2 in frequency, then we only have to worry about going up or down 6 dB per octave. Meaning we can now talk about 6 dB per octave, where the octave represents a factor of 2 in frequency change. What's A above middle C in frequency? Anybody know? Oh, I'm sure we have some musicians in here. That's 440 hertz. It's like one lap around a track, 440 yards if you were way back in the English system of running a quarter mile. But it's 440 hertz. If we now wanted to go an octave higher, now we have the A above middle C, and that A would be at 880 hertz. If we could sing, we could all, but I kind of have a congested voice, so I won't sing today. Yay! But that's a change of an octave, a factor of 2. Let's now just look real quickly at where this 20 dB per octave and 6 dB per, 20 dB per decade and 6 dB per octave come from. And these particular amounts are associated with a single linear factor. Now we just said an octave change in frequency was a factor of 2. let's see what happens if we look at two different scenarios. If we now had a pure integrator, which would be this system, h of s is equal to 1 over s. Then that's one pole at the origin. That's a single factor. And if we were looking at that in the frequency domain, we would look at this 1 over j omega. Now, if we're interested in its magnitude, let's say that we just pick a value. And we say, okay, find its magnitude. Well, in dB, we now have this 20 log of 1 over omega naught. That's its magnitude in dB, which is now 20 log using the power of logarithms. We can say, oh, we're dividing. We can now just subtract those two numerator and denominator terms. What's 20 log of 1? 0. So now we have 0 minus 20 log of omega naught. Suppose we wanted to look at what happens to the magnitude when we're an octave beyond that. An octave beyond that now is saying, oh, let's look at omega 2, let's say, which is 2 omega naught. Well, in terms of its magnitude, that's 20 times the log of 1 over 2 omega naught. But now if we do the same analysis that we just did, we have 20 log of 1 minus 20 log of 2 omega naught. This was 0. But now we can take that last term and break it into two parts, because it's the product, and the product is just the sum of those two parts. And now what have we done? Well, this is where we began with omega naught's magnitude. That was the original magnitude that we started with. And how has that been changed? It's been changed by a value of minus 20 log of 2. And what did we say log of 2 was? We said this was 0.3. This 20 times 0.3 gives us 6. And this whole thing now is our minus 6 dB change from where we started. And that's where this minus 6 dB per octave comes from for a given single pole factor. And you can see that if you change that to a 0 factor, this would now be plus, and you'd be going plus 6. And if you changed it to a decade, your omega sub 2 would be 10 omega naught, and a 10 would be floating around here, and you know what log of 10 is. That's now 1, so now you have a minus 20 dB beyond where you were. So that's where this plus and minus 6 dB per octave, or plus and minus 20 dB per decade is coming from. Is that clear? And you don't have to hear me sing in order to remember that. All right. Now, that's the magnitude of a pole or 0 at the origin. That's just a straight line. It never breaks. It's either always going up or always going down. What's the phase look like? This is now our expression that we're playing with, and we want to know what's the angle of that look like. If we come down here and we say, okay, now that we understand what the magnitude of that pole or 0 looks like, let's look at its phase. We now have the phase of h sub 2 of j omega. But that's now just the angle of j omega to the plus or minus n. But that plus or minus n, what does that do for us? That exponent That just sort of increases however many angles we have, right? This gives us, or another way of thinking of that is it just plops a bunch of these on top of each other. And each one has the same angular contribution. Meaning we could also rewrite this as plus and minus, and now, well, I don't want to write the n just yet. What's the angle of J? Pi over 2, or 90 degrees. And we simply have plus or minus 90 times n, depending on what n is, whether it's a 0 or a pole factor. Meaning we now have plus or minus 90 n degrees, and that's a constant value for all frequencies omega. If we were with the negative, that's if we had poles, and the positive if we had zeros. And all of that is hinged on this picture. If this was our S-plane, here's our real part and our imaginary part. J is just right there, isn't it? This is J. And we want to know what's that angle of J relative to the positive real line, and that's just a change of 90 degrees. And if you had two of those, then you would have two such terms, and that's where the n comes in. You would just be going to 90 twice. If that was a 0, then you would just be saying, oh, that's in the upstairs, or in the numerator, that's a plus. And if it was a pole, now we have the same angle, it's just a pole is coming from downstairs, and that's why we're subtracting it. And that would give us our minus 90 n degrees for all frequencies. Let's now sketch what we've just hopefully convinced ourselves happens when we have these poles and zeros at the origin. First, we need to sketch our axis. Ouch. That's supposed to be straight and flat. You can do much better. You could probably even get out a ruler. Wow. That's supposed to be flat. And now we need to mark it off. Let's say there's 0.1. Here's 1. Here's 10. Here's 100. That's probably good enough. And now let's say that we want this to represent the magnitude in dB. What you may want to do is actually give yourself some guidelines. Let's say that's 20 dB. Let's say this is 40 dB. And this is 60 dB. And you could have the negative of those. You could say here's minus 20. Wow. Here's minus 40. Minus 60. What do we know is happening if we're sketching the magnitude of a pole or zero factor at the origin? We can pin them down, can't we? No matter what slope they have, they all are going through exactly the same single point. And that point is when omega is equal to 1, or 10 to the 0, and we have a magnitude of 0 dB. All of these straight lines will be passing through that point. Suppose I say, oh, let's say that we had one pole at the origin. So now we just have a pure integrator. What does the Bode plot magnitude look like for a pure integrator? It's sloping down, isn't it? Because a pole is downstairs. So we know we have a negative slope from left to right, and it's only 1, so we just have to do minus 20 dB per decade. which means from here we can go down 20 dB at 10. So we would be right here. Then we could go to 100. What do I do to the left or for lower frequencies? Is it flat? No, that's what I'm trying to make sure you're clear on. This thing never breaks. If we go a decade to the left or lower in frequency than 1, we're at 0.1, but now our magnitude was sloping down, so this one actually needs to be 20 higher than it was at 1. Meaning now we would be right there. And our straight line would look something like this. This would be then n equal to -1, or 1 pole. If I had a 0 at the origin, it's just the opposite. Now I'm going, whoops, wanted to change colors. Now I'm going up, aren't I? But I also have to make sure that I'm going up always and never starting that up behavior. I'm always going up, meaning now my sloping line, and that's supposed to be a straight line. This now represents n equal +1, or 1, 0 at the origin. These are origin factors. Questions on that? Yes?
Put in gain factor as well. Would that be, say you had that phrase where the zero crosses?
Now the question, you're getting ahead of us. But yes, the question was, what happens if you have a gain? Right now we're saying we have just a pure polar 0, and the numerator is 1, effectively. But the question was, what happens if our numerator has a gain in it? Maybe it was 5 over s. What does that 5 represent? That was a change of 14 dB, wasn't it? That means that if we had 5 over s, instead of this blue curve representing our true Bode plot magnitude response, now every point here would have to be vertically raised 14 dB, which means, oh, instead of it crossing 0 dB at 1, it's actually crossing 14 dB, the whole thing. So you could draw this blue, then you could draw the magnitude associated with the constant, which is 14, and now add those up point for point in terms of frequency, which effectively what you're doing is you're simply raising this, or you're translating this blue curve up 14 dB for all frequencies. Is that clear? That's what happens when you have a gain or a constant and a pole at the origin. And you're going to have that. What we were sketching here, what was our numerator factor? 1, because the log, 20 log of that was equal to 0, and that didn't change our behavior. Now if I said, oh, you have 0.5 over s, now you're going to go down, aren't you? So this blue curve is going to still be sloping the same slope. We haven't changed the slope. It's just everywhere going to be shifted down by 20 log of 0.5. So now we're 14 dB below where we were with that blue line. And you could do the same thing if somebody said, oh, I actually have 2 poles at the origin. Now I'm going through that same point, but instead of being at -20 at 10, where am I? If I had 2 poles at the origin. Now I'm way down here. And at 100, I'm down here at 80 below. That's pretty cold, isn't it? 80 below. Yeah, I don't think we know what that is in Tucson. We are more likely to know what it is to be 80 above, right? And that we would be where? Not at 0.1, but at 0.01, or 10 to the minus 2. Now we're up to 80 because we're still sloping down. We haven't kinked anywhere in that pole at the origin, or in this case, 2 poles at the origin. So if I could sketch this, and that just keeps going and going, and it keeps going up, this is now the case for n equal minus 2, or 2 poles at the origin. What's the gain? What's the DC gain of a pole at the origin? What's the DC gain? So now think a little bit. Where is DC on this horizontal line? I want to make sure this is clear. DC is omega equal to 0. What are you kind of wanting to say? You were kind of wanting to say omega equal to 1, weren't you? But think of 0, and where is 0? We never get to it, do we, on this logarithmic axis? We just keep going. I say the South Pole. And luckily I was going south when I was going towards 0, right? So this classroom, I picked it specifically so that we could do Bode plots in here and use the Earth as our reference. Now, if we are going all the way to the South Pole, what's the magnitude at DC? Infinity, isn't it? We don't really have a bounded gain. It's infinite when we have a pole at the origin, and that's what this is telling us. And that's maybe what you want to get rid of certain kinds of behavior in a circuit. You might want really high gains at low frequency. And that pole at the origin is going to allow you to accomplish that. Is that clear? Now, what about the phase? What's the phase plot look like? First, we start with our straight line, don't we? And that would be, let's say, and that should be lined up with our magnitude axis, which it probably isn't since I've already slid it off the screen. But now this is, let's say, 0 degrees, and we could put in some guidelines and say, okay, here is, let's say, plus 90 degrees. Here's plus 180. Here's minus 90. And minus 180. Now, where would I put the phase response or the phase behavior of one pole at the origin? How would I sketch one pole at the origin's phase? I have one pole, and I want to sketch its phase. So what points do I want to try to find or identify? Do I need to find some points and then connect the dots? I'm trying to confuse you. It's flat, isn't it? And it's downstairs, and it's at minus 90. This is now the n equal minus 1 angle, or phase plot. That's pretty easy. That's pretty quick. And that's due to one pole at the origin. If I had 1, 0 at the origin, what would that phase sketch look like? That's just up here, isn't it? That's 1, 0. And if we had 2 poles at the origin, now we're down here at minus 180. Questions on that? All right, now it's time for the quiz. I want you to sketch the Bode plots of G of S equaling 10 over S. Now, if you're trying to think what that represents, this is a system. In the time domain, if somebody wanted to say, well, what really is going on in the time domain if you have a transfer function G of S of 10 over S, in the time domain, you could think of this as a signal x of t. It gets scaled by a gain of 10, and then you just integrate it, and out pops y of t. Now, is this system BIBO stable? I would say no. A lot of times books will say it's marginally stable, but that's only if you sort of are exciting it with an initial condition. What would be a bounded input x that would cause this output to go unbounded? Just any kind of constant, wouldn't it? Any constant would, if you now integrated, if you put in a constant here and integrated it, what's the output going to do? Just going and going. It's going unbounded, isn't it? I want you now to sketch the Bode plot of 10 over S. Everybody get an answer, or you know how to sketch it if you didn't sketch it? What's the DC gain? What's the DC gain of this system G of S? DC gain? You're giving me the gain of the constant, aren't you? So I want to make sure that we're clear on this. We do identify constants, and we find the gain of that constant, but that's not necessarily the same as the DC gain. It's not going to be the same if you have poles or zeros at the origin, and I want to make sure that's clear. That's then maybe a trick question, but if you just replaced S with 0, you should be starting to scratch your head and going, something's not right, I'm dividing by 0. Well, you're blowing up. If you now sketch a pole at the origin, you're never going to get there if you're walking to the South Pole. That just keeps going up and up and up. I would say it's undefined or it's unbounded. What I want you to realize is that the constant, which you may have factored out and said that's 10, and the DC gain, those can represent two different things, depending on what you have. Meaning the constant and DC gain may not be the same. In this particular case, if you were sketching the magnitude, you really sort of have two pieces, don't you? You have a constant piece, which is 20 times the log base 10 of 10, which is 20 dB for all omega. And what's the phase of the constant? And that's 0 for all frequencies. Now we have this pole at the origin, and there then are two terms. We had a constant term and a pole at the origin. This now always has a slope, and since it's a pole, it's a negative slope, and it's minus 20 dB per decade. That's the slope. But you have to know where to put it down on your chart, and that you could say is fixed by saying, well, that sloping line will pass through 0 dB at omega equal 1, where I'm now dividing this up into a constant piece and a pole at the origin piece. And then the phase, this was the magnitude response, wasn't it? So this was the magnitude of the pole at the origin. Its phase, since it's a pole and it's just 1, it's minus 90 degrees for all omega. And to sketch this, we have our magnitude sketch. We could say, okay, here it is. Here is our independent variable, omega. We have, let's say, 10 to the minus 2, 10 to the minus 1, 10 to 0, 10, 100. And we have the appropriate guidelines. The pole at the origin would be going through 0 dB, and then minus 20, minus 40, and minus 60 all the way out here at 1,000. That's just the pole at the origin. What's our gain look like? It's just this straight line, isn't it, at plus 20 dB. So this is our gain. This was our pole at the origin. And to actually sketch the total magnitude of G in dB, we now need to add these up point for point at all frequencies. Meaning right here we add 0 and 20 to get 20. Then we add the blue 20 and the black 20, and we get 40 at 0.1. Likewise here, we add 40 and 20 and get 60. At 10, we now have 20 and minus 20 or 0. At 100, we have minus 40 and plus 20, or we now have minus 20. And our total then, magnitude sketch, should be parallel to that black line, and it should just be 20 dB above that black line. This is now the magnitude, or the total magnitude response. Questions on that? The phase is not nearly as involved, is it? The phase, we have still two pieces if we wanted to. But now one of those pieces is just stuck at 0. The constant is giving us 0 dB, and the pole at the origin gives us minus 90 degrees. And this is now the total phase. It's always minus 90 degrees. And if I said, what's the phase of G of S equal to 10 over S at omega equal to 100, you could say minus 90 degrees. And I could say, okay, for 2 more points, what's the phase at 0.1? Minus 90. Questions on that? Let's now look at sketching the next piece, which is the linear terms. And I'm differentiating between these linear terms that have breaks and those poles and zeros at the origin. For example, let's say that somebody gave you a transfer function h of s of 1 over s plus 25. What is that behavior-wise? Pardon? It's a low-pass filter, isn't it? You could find the DC gain. What's the DC gain of this one? 1 over 25. Well, let's now put this is in pole 0 form. Let's put it in time constant form by factoring that pole value out. And now we could write this h of s equivalently as some constant 1 over 25 over s over 25 plus 1. And what I'm going to do then is I'm going to be playing or describing this h of s in the following way. I might write this, if it was a pole factor, I could write it that way. It was just 1 over s over 25 plus 1, where this 25, that was the pole, but we're going to probably refer to that as the break frequency. Or somebody might refer to something similar to that, and they may say, well, I like it to be referred to as a time constant. And if that's the case, now we would identify this 1 over 25 as the time constant associated with that pole factor. This is now the tau or the time constant. Meaning now, if I start talking about this generic linear term or linear factor, based on that example, hopefully it's clear that I could rewrite any linear factor, h sub 3 of j omega, as some j omega tau plus 1 to the plus or minus n. Meaning here, I'm simply replacing s with j omega, or s with j omega. And if I do that, omega is my variable frequency, or my independent variable, and tau is the time constant. Or if you wanted to write it in terms of the break frequency, which is usually what I prefer, we could now say the linear factor can be expressed as j omega over omega naught. This omega naught is our break frequency. If we now wanted to look at the two pieces of this, like we've done before, we have a magnitude term, which is just to take the magnitude and find its value in dB, meaning we now have plus or minus 20 n times the log of the magnitude of j omega over omega naught plus 1. Or I've already factored out in front of the logarithm this exponent, plus or minus capital N, where the dB is 20 log of the magnitude, and now I've pushed that exponent in the magnitude out front. And we want to look at that behavior of that particular expression. We also can think of the phase, and the phase is now the angle of plus or minus n times j omega over omega naught plus 1. Where we're interested now in the angle of that piece, and we'll just scale it by however many of those we have, which is given to us by capital N. And if I now said find the angle of this complex number 1 plus j omega over omega naught, how would you find that angle? If you forget, I would just sketch it in the complex S-plane. We have a real part of 1, and we have an imaginary part of omega over omega naught, and I would just sketch that. So I walk over, on the real axis 1, and then I just go vertical, omega over omega naught. Or you could say, oh, that's just the inverse tangent of the imaginary part over the real part. And the real part, since we've normalized this, since we put everything in time constant form, that really goes away. And now we're looking at this angle of omega over omega naught, or the angle that has a tangent of omega over omega naught. Omega naught is our break frequency. That's fixed, and omega is varying. And we want to know, what does this look like as omega varies? And now we get into Goldilocks. What in the world? Where is Goldilocks coming in? Well, what's the story of Goldilocks? She goes in and she starts checking out some chairs or beds or porridge. Maybe she checks out a chair, and one was what? Kind of small, or maybe we could say it's a little low. The other one was maybe a little big or high. The other one was just right. It was right in the center. It was the sweet spot. Well, that's what we're doing here. We actually want to identify 3 different frequencies and look at these magnitude and phase factors at those 3 frequencies, and that'll basically give us the way that we can connect our dots of drawing straight line approximations. We are trying to then identify three key frequencies. Just to give you a way of thinking of that, or what in the world is he talking about, let's just tie it to Goldilocks. Meaning, we're going to have a low frequency, we're going to have a medium frequency, and we're going to have a high frequency. And the relationships on those are the following. The one in the middle, the sweet one, that's our break frequency. For any of these factors, it will have a break frequency. That's the omega naught. That's our sweet spot. Now, what we're classifying as low are frequencies that are a decade below the sweet spot. So this is a decade below omega naught, or 0.1 omega naught, or that's now omega naught over 10. And the high, then you can guess what that's going to be. That's a decade above, or a factor of 10, bigger than omega naught. Let's now look at these magnitude and phase factors at those three different frequencies. Well, let's just quickly do it, and then we'll go through it a little bit more carefully. What if I looked at the sweet spot here for the magnitude? What do I have? Omega is now equal to omega naught, and I have the real part is 1, the imaginary part is omega naught over omega naught, it's 1. So I have equal real and imaginary parts. I have 1 plus J1. What's the magnitude of 1 plus J1? That's the square root of 2, isn't it? That's actually going to give us then 2 raised to the 1/2. Well, we pull the 1/2 out and we'll have a 10 log of 2. What did we say log of 2 was? 0.3. So now we have 10 times 0.3, that's 3. So at the sweet spot, for a pole, we're going to be actually minus 3 dB down from the straight line values that we're going to find. So the true magnitude will be the 3 dB point at the break frequency. What happens when, is that clear? What happens to our phase when omega is omega naught? At the sweet spot, we have 1 plus J1. What's the angle of 1 plus J1? 45 degrees. If it's a pole, then we're at minus 45 degrees. We're halfway between where we started, 0, and where we're going to end, minus 90. That's at the sweet spot. At the sweet spot, we're at a 3 dB frequency, or location, and we're at a phase of plus or minus 45 degrees, if it's just one factor, 0 or pole. What happens for small or cold porridge? Then we're going to have 0.1 omega naught, aren't we? 0.1 omega naught over omega naught gives us 1 plus J 0.1. So if you're looking at the S-plane and you go over 1 and then you go up 0.1, what's the angle? Really small, isn't it? So we're going to just call it 0. Does everybody see that? And what's the magnitude? 1 plus J 0.1. Oh, we're just going to neglect the 0.1, and now we have log of 1. What's log of 1? 0. So we're saying a decade before the break, our magnitude is 0 dB, and our angle is 0 degrees. What happens now a decade beyond? We know what happens right at the sweet spot. What happens a decade beyond that? Now we said that frequency is 10 bigger than omega naught. Now we have 1 plus J10. Which is the bigger piece, the real part or the imaginary part? Imaginary part. So let's throw away the real part. And now we have 20 log of 10. Well, that makes sense. Now we're just 20 dB away from where we were at the break. So we're either below by 20 dB or above by 20 dB, and that makes sense. It's a linear factor. We're now sloping at 20 dB per decade after the break frequency. So we were flat until the break, and after the break we just go down if it's a pole 20 dB per decade. What happens in our straight line approximation? What we're going to do is we're just going to draw it to the flat to the break, and then after the break we're just going to go with a slope of 20 dB down. Then we know if we want to correct that we will actually be below by 3 dB, and if we wanted to, we could curve fit a smoother line connecting those straight line asymptotic behaviors at low frequency and high frequencies. But we're really just trying to do a real quick sketch of what's happening. Questions on the magnitude? What about the phase? When omega is at the high side, this is now 1 plus J10. So now we go over 1 and we go up 10. What's happened to your neck? Now it's at about 90 degrees, isn't it? And if it was a pole, you've now gone down 90 degrees. So we're now transitioning from 0 degrees, a decade below the break, to minus 90 degrees, a decade beyond the break, and we'll just be flat at those two values on either side of those frequencies. And in between, it's a straight line connecting it. And that straight line will pass nicely through the minus 45 degree point when omega is equal to omega naught, right at the sweet spot. And that's how we're going to approximate the magnitude and phase of a linear factor. Questions on that? So how does Goldilocks play into this? Small, medium, and large, right? So now you could supersize it. If you supersize this factor, now you're saying, oh, you're now, let's say, at the big side. You're now a factor of 10 beyond the break. And what would your phase be? If it was a pole factor, minus 90, wouldn't it? Now you can start looking at these factors just in general. If I said, suppose that you have this transfer function, and you've already told me it's a low-pass behavior, this 1 over s plus 25. Now I say, what's the phase of that transfer function for low frequencies? And you might raise your hand, Dr. Tharp, what's a low frequency? And I'll just look at you. And I'll say, what do you mean, what's a low frequency? You know what a low frequency is. I just read you the Goldilocks nursery rhyme or whatever. Right? What is low frequency in this particular transfer function? What are we considering to be low? A decade below this break, isn't it? So anything below 2.5 we would consider low. So if I said, what's the phase at a low frequency, you would say, oh, low frequencies are any frequencies less than 2.5. That's just our sort of common behavior that we're talking about. And what would the phase of this be? If you passed, and what's that telling you? Now, if you injected a signal of a low frequency, let's say the low frequency is 2 radians per second. So now I give you cosine of 2t. and I say, what's the phase going to be in the output? It's 0, isn't it? So what does that mean? That means the input might look like this, and the output is pretty much aligned with the input. There's no phase shift. There's no delay at that frequency. As we increase the frequency, if I say, well, what's the phase at the break frequency? Minus what? So you need to be clear on this. At the break frequency, what's the angle? Minus 45. Now I say, what's the angle at high frequencies? Minus 90. Does everybody get that? And now if I said, oh, what's the magnitude at low frequencies? 0 dB, isn't it? Which means that if I gave you an amplitude of 1, the output is going to have an amplitude of 1. It's not going to be attenuated because our gain is 0 dB. Whereas at higher frequencies, if I said, oh, what's the magnitude of this transfer function at high frequencies or at 250, now you're 20 dB below that. But what's 20 dB represent? A 10 factor. So you're 0.1 of where you started, roughly. So if I gave you a 1 for an amplitude on a cosine of 250t, you've now shrunk down to a tenth of that. You're now at 0.1 at 250t. And you're shifted in phase, so you're out of sync by 90 degrees. We'll pick up at that point on Tuesday.